sitting on, I'll just say this is a ball sitting on top of a wall, okay? So we got an object sitting on top of a wall, and if you want it to be like kind of Humpty Dumpty-ish or something, and this thing is going to have a great fall, that's totally fine. But we got this object that's sitting up here. What I would say is that when it's at the top, it's got gravitational potential energy. And you can kind of tell by the title that we're dealing with gravitational potential energy and kinetic energy. And when it falls, does it have any speed? Makes sense, right? So it's going to hit the ground with some speed. And that arrow isn't a force, it's an indicator that there's some speed. The way that we talk about total mechanical energy, though, we talked about the total energy at the top. Maybe I'll call the position at the top position A. Maybe I'll call the position at the bottom position B. I would talk about the total energy at the top as being a sum of all the energies that that object has. Now, for us, we're only going to talk about gravitational potential energy and kinetic energy. We've already outlined that there are like many, many different types of energy, right? But for us, we're only going to focus on those two different types of energy. Kinetic energy, translational kinetic energy specifically, and gravitational potential energy. So at the top, there would be gravitational potential energy at position A. I'll use subscripts to indicate that. And there would be kinetic energy at position A. Now, depending on where you learned physics, there are going to be people that talk about gravitational potential energy as EG. If you have a family member or a loved one that's tutoring you in physics, maybe you even hired a tutor, there's a good chance they're going to use capital U for gravitational potential energy. Oh, yeah. I'm going to use E sub G because it's nice and descriptive and people seem to have an easy time with it. But if you're talking with a family member, maybe your mom's an engineer or something like that, she's going to use capital U probably, okay? Depending on where she learned how to be an engineer. Likewise, if, I don't know, Uncle James or somebody is your tutor, kinetic energy oftentimes will be written as just a capital K. And I talk about this mostly because there's a lot of people in grade 11 that have tutors, but also a lot of people are going to go places like Khan Academy or different online video sources or whatever, and I want you to know that, yeah, I'm aware that capital U and capital K are variables that are stand-ins for the same thing, okay? I'm going to use the E sub G and E sub K because it agrees with our textbook a little bit better. That's the only reason, not because I think it's better or that it's the only way. So let's just be really clear about that. I know that people, well, you know, physics is a global endeavor, right? So we kind of need to know that there's different accents to how people communicate. That's an accent difference. It's not a language difference, really, okay? All right, so as I look at this E total, EGA plus EKA, when it hits the ground, there's going to be E total at position B, and I'd write that as EGB plus EKB. Thing is, if I have balls sitting on top of a wall, what's the kinetic energy at the top? You know this. Zero, because it's what? Got a velocity of what? Zero. Velocity of zero, kinetic energy of zero. So in this special case where it's sitting on top of a wall or an object sitting on a shelf, kinetic energy is zero. When it hits the ground, if there's a height of zero down here, what's the gravitational potential energy going to be? Zero, because gravitational potential energy is based on height and gravitational field intensity, but height, okay? Now in this situation here, I'm going to use different indices. When I say indices, A and B were my before and after for the first one. 1 and 2 are going to be my indices for this one, before and after. And again, this is a question of different physics accents, not right or wrong. Sometimes people use situation A versus situation B. Sometimes people will say situation 1 versus situation 2. Sometimes people will say I for initial and F for final. And there's even more different variants. But I'm just going to stop at 1 and 2 for this one, okay? Anyway, when this thing hits the ground, what would you say about its speed compared to the earlier version? Yeah?
It's
Less. You know, I'm going to indicate that visually by a smaller arrow, okay? And we know that. We've dropped things. But we could still come up with an expression, E total 1 equals EG1 plus EK1. E total 2 equals EG2 plus EK2. And I recognize that if it started from rest, EK1 would be 0, and if it hit the ground at a height of 0, then EG2 would be 0. But there's this thing called conservation of energy. And if conservation of energy is a thing, then what we're really saying is that assuming that there's no energy loss between the top or the bottom, like energy didn't get lost to the universe somehow, energy is conserved, energy conservation is stated like this. E total initial is equal to E total final. E total 1 is equal to E total 2. And in the case of conservation of energy with gravitational potential energy and kinetic energy, this mechanical energy conservation, we'd say Eg1 plus Ek1 adds up to being equal to Eg2 plus Ek2. In our specific case, Eg2 was equal to 0 and Ek1 was equal to 0. But on the whole, this is generally going to be true. And we give a name to this statement. This statement about the total energy before something happens being equal to the total energy of a system after something happens is called the law of conservation of energy. Now, this specific one, because there's only one object involved, I might say it's the law of conservation of energy for a one-body mechanical system. But broadly speaking, whenever the initial energy is being claimed to be equal to the final energy, we're talking about the conservation of energy. This happens to be a one-body mechanical system. And like the same thing is going to be true for, this is a kid that's on a spiral slide. This kid starts off at a certain height, and they end up at a height of 0. The fact that we didn't drop the kid off the ladder, which is kind of what happened to the ball, it kind of got dropped off the ladder, right? This kid takes a journey around a corkscrew-shaped slide. They're still going to have conservation of energy. They're going to have an Eg plus Ek at the top. They'll have an Eg plus Ek at the bottom. And if this was like a perfectly slippery slide with no energy loss due to friction, then the total energy at the top should be equal to the total energy at the bottom. Does that make sense to everybody? Conservation of energy, right? Like, so we've done this. We've lived it. And I think everybody in this room has been on a slide before. So like, this is relatable, right? I mean, for me and my kids, there was a time where the CNE I think in March, they opened up all of their rides. You know, like the carnival rides they have at the CNE? And they opened up all the rides, not outside, but they had them in a big warehouse. I think it was like the Farm and Agriculture building, but they had all the kids' rides inside of there. And you could, for $25, you could go on as many rides as you wanted. And we just rode on the rides. And the crazy thing was, the thing that my kids wanted to go on the most, there was all the round and round rides and the mini roller coasters and whatever. But the thing they wanted to go on over and over again was the, whatever it was, 2 or 3 story tall slide. You know, the one that is never worth it when you're just paying with tickets because it's just a slide with a crazy carpet? You're like, I can go tobogganing in the winter with that. But in March, when the tickets were basically, like unlimited, all they wanted to do was a slide over and over again. But conservation of energy is what I was thinking. It was fun, yeah, it was fun. You know what I didn't like was the guy that did, the round and round one that has like the arms and it's like an octopus? The guy that was running the ride thought he was doing me a favor, and he let me go on there for triple the normal amount of time. I felt like throwing up. There was no favors being done there. He was giving me the thumbs up, and I didn't want to be weak, but I really did not feel good afterwards. I'm not going to lie. All right, so this idea of dropping a mass. We're going to go from position 1. We're going to go down to position 2. Let's give some numbers to this. Let's just say that this mass is 10 kilograms, a nice round number. And we'll say that it drops by a height, like it goes down, a height equal to 5.00 meters. And I know like with projectile problems, we've dealt with like firing things off of cliffs or whatever. This is not firing something off of a cliff. This is just dropping something off a ledge. Okay, we're dropping it. So I'll write that in. It's a drop. It's not a projectile. I mean, I guess that's the simplest kind of a projectile, but we're just dropping it, okay? And so what we could say is that at the top, E total 1 is equal to EG1 plus EK1, same thing as what we've been saying before. And at the bottom, E total 2 would be equal to EG2 plus EK2. And same as we've been saying before, that EK at the top is equal to 0, EG2 is equal to 0 at the bottom. It's fallen by 5 feet. The mass is still the same at the top as it is at the bottom, but the height is different. Now, in this EG1, the EG1 would be dependent on height 1. EG2 would be dependent on height 2, which is when height is 0, right? So we're just like recognizing that would be a thing. If I were to do a lift, on the other hand, I want to give myself a little bit of maybe a break on my page, just to say that there's a left column there and a right column there. If I were to do a lift, like lift this object up, I'll write the word lift. The way that I think about this is like a free body diagram. And we talked about the work to lift something before, but I just want to talk about it like this. I want to say, hey, there's Fg going down, there's a force applied going up, no doubt about that. There'd be a displacement. Essentially, the displacement goes straight up. So I can say, okay, delta D is straight up. And I know that the force applied, if I lift at a constant rate, the force applied is going to be equal to the force due to gravity. And let's just say that my displacement, delta D, I can say that it's in the y direction because I'm so hung up on projectiles and stuff, but I can say that there's a displacement upwards of 5.00 meters. And I say, you know what? I'd like to figure out how much work it takes to lift this. And I think that we did some work calculations with lifting something into the back of a pickup truck once before. This is exactly the same kind of thing. We're just kind of revisiting it. We're saying the work that would be done by this lifter is equal to force times displacement times cosine of theta. And real quick, I know that the force in this case would be equal to mass times acceleration due to gravity. At least the magnitude of it would be. I would say that I'm dealing with just the magnitudes, because remember, I don't need to deal with reference frames. It's just the relative angle between the force and displacement that I care about now. My displacement, magnitude, times cosine of theta. And as I look at this, what's the angle, what's the theta between the applied force and the displacement? Yeah? 0 degrees. Yeah, look at that. Theta equals 0 degrees. Applied is up, displacement is up. They're collinear. They're going in the same direction. 0 degrees. So anytime I have a cos of 0, it's equal to exactly, cosine of 0 is exact, yeah? 1, yeah. So my head math tells me that guy's going to be a 1 right away. Simplifies things just ever so slightly. And then I could sub in my values. 10 kilograms times 9.81, 1 meters per second squared, times 5 meters. What is that, like 490 or something like that? What is it? 490.5, all right. Thank goodness for friends with good calculators, eh? 490.5, and then what units? Yeah? Joules, yeah. Joules. And we could round it off to 3 sig figs, I suppose. Be 490 joules approximately. We're just rounding away the 5, so it rounds even. Now, the thing is, this happens so often. People lift things up into trucks, they put things on ledges or shelves or whatever, and we're essentially storing energy in that object when we lift it up. We give it a name. And this energy, look, every time I lift something, isn't the cosine going to end up being 1 if I lift it straight up? Every single time this is going to happen. So if I break it down, really every time I give this kind of energy, lifting something up into place, I'm going to be multiplying mass times acceleration due to gravity times delta dy. And I'm just going to let you in on this. This is literally the definition of gravitational potential energy. This is the gravitational potential energy formula. Every time I lift something, it's going to end up being this. You know, sometimes people will write it like this. They'll say Eg is equal to mass times acceleration due to gravity times height. Because the height that you lift it to, delta dy, right? So they'll write it one of those two ways. You know, if we talk with our friends and family that learn physics in other countries, or maybe at the university level, they might say capital U is equal to that. But again, this is just a different accent. It's not a different language, right? Anyway, this is gravitational potential energy. Because we've been dancing around what gravitational potential energy is, but we didn't have a formula yet. Yeah. Why did I put a dash? Oh, because that I put a dash over the 0 because the 0 is significant because I was rounding to 3 significant figures. Yeah.